Okay guys, so today we're going to have a bit of an introduction into uniform circular motion, which is the start of topic 1.3. Now, to get us thinking about this, I want you to imagine we've got some kid here who's got some ball on a string. They're spinning it around them with a uniform speed, we'll say, so the speed staying constant, and then at point P the string breaks right about here. I want you to think about which way the ball might go. Do you think the ball will go up like this? Is it going to go kind of in this direction? Is it going to go up this way? Is it going to go straight out like this? Is it kind of going to keep going this way but also continue going around a bit? Is it going to keep going in a circle, or is it going to move back towards him? Right, so just stop, have a think, see what you predict, and we'll maybe get back to that one a bit later. So when we're talking about uniform circular motion, we're talking about when an object is rotating around some point with a radius of r, and it's going to have some velocity v. When we're saying uniform, we're saying that this value of v remains constant even as it rotates around the circle. So so that the length of that vector as it moves around is the same, but the direction obviously has changed. Now, what I want us to consider is I'm going to draw the same object, and it's moving, so it's got an initial velocity here, and then we're going to look at it a fraction of a second later, or at a very small time interval. Really, the smaller the better, and so a little bit later it's going in this direction here. And note that the direction is the kind of tangent or perpendicular to the circle, so it's going to, the vector is going to be moving in that direction like that. I might draw that a little bit more clearly down here. So it's got some initial velocity vector, then it continues moving around. The length of the vector stays the same. Obviously the direction has changed. Okay, now knowing that we've got a final velocity and initial velocity, we can use this to calculate change in velocity. So I'm going to, just as a reminder, so change in velocity is always given by Vt, take V naught. And we can represent that with a vector, which is going to be delta V equals Vt plus negative V naught. And for these two here, remember this should be really the tangent. If I had Vt, it's going to look something like this. And if I add, so this is Vt, add negative V naught, which is going to be the same as V naught in the opposite direction. That gives us a resultant vector, delta V, which is in this direction here. And if we think of acceleration as change in velocity over time, and the acceleration is going to be in the same direction as the change in velocity, this tells us that this ball is actually kind of has got acceleration in towards the center of the circle. Alright, and what we call this is centripetal acceleration. Okay, and centripetal just means center and seeking, so center seeking acceleration. So even though the velocity magnitude is staying the same. Because it's changing direction, we have got acceleration. Okay. Now we kind of need a way to relate. This to the radius of the circle. So I'm going to add some things in. If it goes through some angle theta, and we'll call this point A and point B. Got radius R. I'm going to define the length from here, from A to B along the arc. Okay, along the arc as delta L. And we can also think of the distance between A and B in a straight line, which kind of look like that. And they're ever so slightly different. But as we decrease the time between these 2 points, this angle theta is going to get smaller and smaller and smaller, and the magnitude of delta L is going to approach the length of AB. Okay, and what we'll see is this actually creates a set of similar triangles. So this triangle over here is going to have an angle theta here, just like here, and it means we've got a relationship between the side lengths that we can compare on the two. And for our intents and purposes, we can say the relationship between delta V and V, and it can be, because this V I'm relating to either the initial or the final, and they're the same in magnitude, it doesn't matter which we choose. So the change in velocity, which is this length divided by this length, is going to be the same as kind of this distance here, which we're kind of approximating with delta L divided by R, which is delta L on R. All right. Now, the delta L is really a measure of the distance that this ball has gone in this very short amount of time. So another way we could think of this is really velocity multiplied by time over the radius. Now what we can do is we're just going to rearrange this to show if I multiply both sides by V, we get delta V equals V squared T on R. And then if I divide both sides by T, we get delta V on T equals V squared on R. What's cool about this change in velocity over time is simply acceleration, so we can rewrite this as A equals V squared on R, which is pretty awesome. So now we've got, and this is a formula for centripetal acceleration, and this is that center-seeking acceleration. Okay. And sorry, I just had a phone call. So the next thing we need to know is, well, what's the velocity? So velocity we can always think of as distance over time, which equals, in this case we're kind of thinking about the distance that's gone around the circle, which would be 2 pi r divided by the period. Okay, remembering that t equals 1 over f, so the period equals 1 over the frequency. So we now can work out the velocity as long as we have the radius and either the period or the frequency. So let's have a shot at doing that. So I've got a question here. A ball is revolving uniformly at the end of a string. In a horizontal radius of 0.600 meters. Makes 2 revolutions per second. What is its centripetal acceleration? Okay. So as usual, I've started pulling out the values, and I thought maybe I should wait until we've done this on the video. So I've pulled out the radius, the period here. So it makes 2 revolutions per second. So that means it's got a frequency of 2. So the period is going to be 1 over 2, or 0.5. The velocity is unknown, but we can now use our kind of new formula that we've just come up with, which is 2 pi r on t. Okay, so that's going to give us 2 pi 0.600 on 0.500, which equals 7.5454 meters per second. Using this value, we can now substitute that into the acceleration formula. So a is now unknown, so a equals v squared on r, which equals 7.54 squared on r, which is 0.600. And annoyingly, I've put my calculator away, so and I didn't calculate this one beforehand, so I'll let you finish that one off yourself. But yeah, that's it. That is your introduction to uniform circular motion, in particular centripetal acceleration. Hopefully by now you've had a chance to think about the direction that the ball is going to go in. So if it breaks right here, the ball is going to continue in a straight line because it's no longer got any forces acting on it to push it back towards the center of the circle. So because it's got no forces acting on it, it's going to continue in a straight line. Good job, guys. See ya.